Hi guys, on to the second day of 4.1. So we're going to be doing problems really similar to what we did yesterday. So today we're going to start by looking at the differential equation. And it's just an equation that has a derivative in it. That's all that this is saying here. There's the chapter 6 in our textbook is dedicated to this. So we're just starting to get exposed to this. We'll look at it in more detail once we get to chapter 6. So what we're going to do when we solve a differential equation is we're going to find the original function from which the derivative came. So very similar to what we've been doing, the directions just look a little different. Remember the general solution, we talked about this, it involves plus c. So we were adding c onto everything because we said the derivative of a constant is 0. So this c could be anything. Today, though, they might ask us for a particular. And what that means is we are going to say it is the solution. So we're going to find a value of c. And I'll show you the difference on when we know we're looking for a general or when we're looking for a particular. Okay, and a lot of times they spell it out for you. Like look at example 2, for instance. So this is a differential equation. You can see the derivative. We'll go back up here. A differential equation has a derivative in it. Look at the derivative is this, is 2x to the negative 3. So this is definitely a diffie-q. Now to find the general solution, they said that it can have a plus c at the end. Okay, so when if we're given the derivative, we know we need to integrate it in order to get the original function. So what we would do is whatever we do to the left, we do to the right. And I'm going to show you 2 different ways this works. So I'm going to integrate dy dx. And remember, we always need to put the dx there if that's our variable. So all I did was insert, let me write it here and then it'll disappear. You insert an integration and then the dx. And then you're going to do the same thing over here, 2x to the negative 3 dx. Now on the left, let's think about what this is saying. Okay, we know how to do this. This is what we were doing yesterday. But now we have this new thing on the left. So there's 2 ways to think about this. This is saying, if I have the derivative, what did I have before I had the derivative? Well, you guys know this. What do you have? You have y, right? If I'm integrating with respect to x here of the derivative, you know that you have y. Because what is, if we go backwards now, right? What's the derivative of y? Isn't it dy dx? So we know that this is right. Another way to look at it is over here. So let me go ahead and write this. So this is just a little aside. If you have dy dx and you integrate with respect to x, another way of looking at it is thinking about like those kind of canceling. So now what I'm really doing is I'm integrating 1 dy. So now I'm integrating with respect to y. So if I integrate with respect to y, then this answer would just be y. And look at, that's what I got over here too, right? So 2 different ways to think about it. The first way is if this is the derivative, what did I have before it? And I had the function. The other way is to think about this and integrating 1 with respect to y, which gives you y. Okay, so that's kind of the new thing for today. On the right, we did this the other day. We know that we write 2, we add 1 to this, divide by that power, and add a c. Now we're not allowed to have negatives exponents, so this is going to be negative 1 over x squared plus c, and this is our general solution. Remember, general solution has a plus c, and so does ours, so we're good. Okay, next one. Now it asks us to solve the diffie-q given that they gave us the second derivative and then they gave us these values. Do you see these values here? What that means is it's going to allow us to find our c values. So when they're asked to solve the differential equation, what they really mean is find y, in this case that it's equal to f of x. Well, they only gave us the second derivative. So think about how are we going to go from the second derivative to the original function? Well, where can you go? If you start with the second derivative, can't you get the first derivative? Oh, maybe you're seeing it now. And then if you have the first derivative, then you can back into the original function. Okay, so this is going to be a 2-step process. First, we're going to find f prime. How are we going to do that? Well, we're going to say f prime is found by integrating the second derivative with respect to x. Okay, so we're going to take this. We are going to add 1 to the exponent, divide by that number, and plus c. So now we can say the first derivative is 3x squared plus c. Now this is a general solution. But look what they told us. They said when the input is 1, the output is 5 of the derivative. So we can come over here and say when the input is 1, the output is 5 of the derivative. Okay, now we're able to go on and solve, and we can see that c is 2. So f prime of x, which we found above, was 3x squared plus c, but now we know c is 2. So here's the derivative. This is the first time we were able to find a value for c instead of just leaving our answer like this with c, because they told us if you sub 1 into the derivative, you get 5 out. So we went ahead and did that to find our c. Okay, now I started writing the next part. Now we need to find f. Well, this is what we wanted the whole time, right? But now to find f, we know that we can integrate the derivative. So we're going to integrate 3x squared plus 2 with respect to x. So we're going to add 1 to the exponent, divide by 3, integrate 2, you get 2x. Now we have another c. So if you guys have the same problem with multiple c values, what you want to do is you want to denote that they're different by giving them subscripts. So what we wanted to do here is we're going to call this stuff c1, and then we're going to call this c2. Okay, so we're going to do that on this kind of problem where we have two different c's in the same problem. Okay, so now let's clean this up, and we're going to get x cubed plus 2x plus c2. We know we're not going to leave a general solution with c because they told us when you sub 2 into f, you get 6, and here's f. So we get 6 out when you sub 2 in. So now 6 is 8 plus 4 plus c2. 6 equals 12 plus c sub 2. So c sub 2 must be negative 6. So f of x is going to be x cubed plus 2x minus 6. And what did the question say? It said find or solve the Diffie-Q that produces that, and there we go. We just found it. Okay, so this is our final answer. Okay, on to the next and last problem. Okay, now we're going to have particle motion with this on the bottom here. Let's see if I can pull this up. I gave you some notes here just to recall. Remember, position, we use x or s. Velocity is the derivative of position. Acceleration is the second derivative of position, first derivative of velocity. Remember when an object's at its max height, so at this vertex here, the derivative is 0, the derivative of position. And if they say initial velocity, we want to find the velocity when t is 0. Okay, guys, as we read through this problem, I'm going to take notes on it. I think it helps as you read through a particle motion problem to pull out the important data. So we have a golf ball dropped from a cliff overlooking the water. So here's our golf ball, and it's being dropped. Because they said dropped and not thrown, we know initial velocity is 0. Oh, and we're in Hawaii. That sounds great. It's actually snowing as I'm recording this right now. And it's going to hit the water 30 seconds later. Okay, so what that means is the position at 30 is 0. We have acceleration. Okay, so if we look at this, this is the position at 0, this is the position at 30. So how far did it fall? How far? That's a position. We need to get to the position function. And then we have to figure out what time we would be looking at. Well, if you look at this picture I drew, this distance right here is going to be the height of the cliff. That's going to be how far it fell. So we want to find out the initial height. So we're going to try to find s of 0. First, we have to find s of t. But all that they gave us on here is acceleration. So we want to go from acceleration to position, but first we have to stop at velocity. So we're going to integrate acceleration to get velocity. Let's see if I have that down here. We're going to integrate acceleration to get to velocity, and then we're going to integrate velocity to get to position. Okay, so let's start this off. We're going to say velocity is found by integrating acceleration with respect to time. So this is going to give us negative 9.8 t plus c1. Now I'm going to use c1 because I know I have to integrate twice. So I know I'm going to have two c values. Now hopefully we can figure out what c is. If you look up at what was given, they tell you right here that the initial velocity was 0. So when t is 0, the velocity is 0. Oh, and there was actually a typo here. That's supposed to be v of t. Okay, so v of 0 is 0, which is negative 9.8 times 0 plus c1. That makes c1 0. So our velocity function is just negative 9.8 t. But remember, we weren't trying to get to velocity. We were just using that to get to position. So now to find position, we're going to integrate velocity with respect to time. Okay, so if we integrate that, we're going to get negative 9.8 t squared over 2 plus c sub 2. We already used c sub 1. This is now going to give you negative 4.9 t squared plus c sub 2. Now look back up at the notes we took. Do we know any ordered pairs of position? And we sure do. At time 30, the position was 0. So now we go back down here. And what did we say? At time 30, the position is 0. So now 0, if I square 30 and multiply it by negative 4.9, I'm going to get negative 4410. So C sub 2 is 4,410. So now we can say our final position function is negative 4.9 t squared plus 4410. Okay, so that's our position function. But what did they want? They wanted how far it fell, right? And we said based on looking at our picture, how far it fell, that would be the position right here. So we want this distance. So we need to find S of 0. So S of 0 is negative 4.90 squared plus 4410. So that means 4,410 in what units? This is position, and acceleration is meters per second squared. So this is just meters. Okay, so it's everything you guys learned about particle motion, now you're just going backwards. Velocity at impact. So once you guys find the first couple equations, now you're just kind of running through these as though we were in algebra 2, like if we had the formula. The velocity at impact would be velocity at 30. And we know our velocity function, it's right here, it's negative 9.8 times t. So this is going to be negative 9.8 times 30, which is going to give us negative 294. And what would velocity be in? Because acceleration is meters per second squared, velocity is going to be meters per second, and that's negative 294. Okay, and oh guys, under 15 minutes and we're done with day 2. Awesome. Okay, see you later.